And in the last uh, discussion of this Python, I actually go through the Python code of this classify zero function. And this function, if you remember, has 4 arguments. In X here is the point to be classified. Data set is an array of existing points. They have a classification given in the array labels, and K is the number of nearest neighbors. And then we're going to try to take the points in the data set, finds the K points in the data set that are nearest the point to be classified, and then we're going to take those K vectors and find out, look at their labels and find out which label occurs most often. So that's the algorithm implemented in classify zero. And I suspect if you're a Python whiz, which I'm not, you will find this code very transparent. I find it, as I say at the bottom, compact and elegant, but a little opaque. And there are some Python intrinsic capabilities that I would have to go. I had to go to the web to actually find out what they were, and they're not ones that live in my head waiting to be applied at every moment. Whereas most things in most other programming languages, I do not have to do that. All right, so if we just go down this slide and let's look at this thing here, the dataset size. Its dataset does shape of 0. That is the number of entries in the dataset, which would be if I took the whole dataset 1,000. But in the case where I call this from the testing case in the previous slide, it's actually going to be 900 because dataset is only the last 900 entries of the full dataset. And index actually runs through the first 100. Anyway, so it's the number. You don't have to tell it because in some other languages you might tell it the number of points. Here you just use it from this intrinsic shape. The next command is actually we want to find the distance between the dataset points and index. So what we do is we generate a new array, which is actually the same shape as dataset, but the only vector it has in it is index, which is repeated a number of times equal to the number of points in dataset. So that's what this tile command does. It just replicates index a number of times equal to the dataset size. Then we subtract datasets. So now we actually have in diffmat a set of vectors which are just the difference between index and the dataset values. And actually, it's the length of those vectors is what's going to be used in the nearest neighbor algorithm. So we're going to use Euclidean distance, so we have to square the components. That's done here. So this is not a vector square. This is just a component squared. Then we sum over the vector components, which is over the 3 components here, and that's this x equals 1 tells us over which direction to sum over the vector, not the points. Then we take the square root. So finally we have the distances. Actually, we needn't have taken the square root because if you want to sort the value in its square, sort in the same way. But anyway, this is the Euclidean distance. Then we actually call this intrinsic function argsort, and we sort the distances and return the indices corresponding to the sorted distances. Okay, now we're going to set up a little Cunningham dictionary which tells us which labels and which classification values occur in the K nearest neighbors. So class count is a dictionary set to the null dictionary initially. And now we just run over K values because those are the first K entries in the array sorted just indices. We don't care about any of the other entries. And we don't actually care about the value of the distances of those things, because we're not going to look, especially at in the k nearest neighbor algorithm. We do not look at the distances among those k. We just look at those k points and find out which label occurs the most often. So we've lost the distances at this stage; they're not needed. We do have the index values. And we need the index values to find out the label of those k points. So this vote label variable has the label of the k nearest neighbors, and it's as we run over I, we run over those k labels. Then we take the k label, we take in class count, and we increment the count of the label by 1. And this would be programmed differently in different languages, but in this particular language, it's coded in this fashion. And that's because we're dealing with dictionaries, so you have to sort of look up the built-in operators that work on dictionaries. And so this just increased by 1 the number of times this dictionary entry it occurs in the k nearest neighbors. So remember, the dictionary is a set of keys. The keys run over the labels, and then for each key we have a value, which is actually possibly often 0, and that value is the number of times this label occurs in the set of k. So I'm not going to actually, k remember is 3 in the cases recorded, so this is not a very big dictionary. And then so now we have in class count, which is a dictionary for every label we have the number of times it occurs in the nearest neighbor set. Then we do another sort on. Now we have to look up how to sort dictionaries, and this slightly, I must admit, non-intuitive command here, which is again you have to be a Python expert to really get, but it's sort of clear what's going on. We're iterating over all the dictionary entries in class count. We're looking at the number of votes for it, which are the number of times they occur in those k points. That's this operator.item getter of 1. That's because we're picking up the value of each item, and then we sort this. But we want to sort it with the highest number first. That's why we put reverse equals true. So at the end of this, we get a set of dictionary entries which start with the label, which is the key value, and then they follow by the value. But all we care about is the key value. And the first one is the one we want because it's the one that has the most votes. And then we return this particular dictionary entry, which is voted on as being voted positively, namely by appearing in the k nearest neighbors the most times. So as I say, this is typical of this type of language. And that's the end of this particular discussion. And we can just maybe just rotate this for a little bit. That's a sort of final thing here. I mean, plotviz allows you to do rotations, translations. You can change its size. Let's see how we change its size. There we are, changing the size, making it smaller. Sometimes that just makes it easier to rotate, maybe, but doesn't show it so well. And you can either use the mouse or some combination of the mouse. Of course, if you have a zoom thing on your mouse, that will also work well. So anyway, those are the types of things you can do with plotviz, and That's it. Thank you very much.